Welcome to Brain Vision.
In this question, we have a house with a layer of wood, 3 centimeters thick on the outside, and then a layer of styrofoam insulation, 2.2 centimeters thick on the inside wall surface. We're given the K values for the wood and the styrofoam, and we're told that the interior temperature is 19 degrees Celsius, while the exterior temperature is negative 10 degrees Celsius. In part A, we're asked to calculate the temperature at the plane where the wood meets the styrofoam, and then in part B, we're asked to calculate the rate of heat flow per square meter through the wall. So let's start off with just a little diagram to orient ourselves. So let's say that this is our layer of wood, and then we'll have the layer of styrofoam. So the layer of wood is 3 centimeters thick, and the layer of styrofoam is 2.2 centimeters. And then the temperature on the outside, I'm going to call that TH, that was given as negative 10. And then the temperature on the inside, we'll call that, let's call that one TH because that's hot, right? That was given as 19, and then we'll call this one TC for T cold. Okay, and then in part A, we're asked to calculate what's the temperature at the point where the wood and the styrofoam meet, so right in between here. So the idea behind this is that the flow rate of heat, the heat per unit time that is going from the styrofoam, from the interior of the wall to the exterior of the wall has to be constant all through the wall. So the rate of heat flow through the styrofoam has to match the rate of heat flow through the wood. So a way we can write that in terms of an equation is H wood, or HW, is equal to H styrofoam, or HS. And so that's basically because we can't just magically lose heat anywhere, so everything kind of has to be continuous. So using this equivalency, we can go ahead and calculate what the temperature at the inner wall is going to be, because both of these things depend on that temperature of the inner wall. Now, before we do that, I'm just going to list out some givens. So we have KW 0.08. I'm not going to write in the units because everything is in standard units here. The length of the wood is the 3 centimeters, so 0.03 meters. And then the length of the styrofoam, that is 0.022 meters. Okay, so the flow rate of the heat, we can write that for each section of the wall. And that's going to depend on TH minus TC for each chunk, right? So the hot side of the wood part is going to be at temperature T, that intermediate temperature. The cold side of the wood is going to be at TC. And then we have the same equation, different K, different L, for the styrofoam, LS. And this time the T in the middle is going to be the cold temperature, so it's going to be the -1, and then we'll have TH there. Okay, so this A is the cross-sectional area through which the heat is flowing. That should be the same through both sections of the wall. And I'm just going to rearrange this a little bit to make this easier to solve. So on the left-hand side, I'm going to multiply everything by LS. So on the left-hand side, I'll get KWLS. And then I'm going to divide by KS. So I'll get LWKS. And so that'll just leave me with TH minus T. So I can go ahead and plug everything in based on the values that I've already written out. So I'm just going to calculate that coefficient out in front first. So that is going to be 5.87. So that was just all four of those variables came out to 5.87. And we still just have TH minus T on the side. Let's go ahead and fill in those temperatures. So T cold was minus 10, so that becomes a plus 10. And then TH is 19. Okay, so now we just need to solve this. So I'm going to expand out this bracket here. And I'm going to collect like terms. So let's bring that plus T over to the minus T over to the other side. That becomes a plus T. And then I'll bring the 58.7 to the other side. So that's 19 minus 58.7. That gives negative 39.7. And finally, we're just going to divide by the 6.87. So that'll give a temperature right in the middle of the wood and the styrofoam of minus 5.78 degrees Celsius. So that is our final answer for part A. And then in part B, we're asked to calculate the rate of heat flow per square meter through the wall. So we're pretty well set up to do that because basically that's just asking us to, go through and calculate HW or HS per square meter. So you can use either side of the equation here, basically. Okay, so I'm going to use HS, and HS is KS A T hot minus T over LS. Now it is asking for the rate of heat flow per square meter. So we're going to divide each side by A, HS over A, and that's what we're trying to find, which is great because we don't actually have A. So if we had to leave that on the right-hand side, we'd be in a little bit of trouble. So we just fill everything in. So 0.010. T hot is 19 minus 5.78. So that's a plus. And then all over 0.022. So that'll give us a heat flow rate per unit area of 11.3 watts per meter squared. And that's your final answer for part B.